Good morning, everybody. It's always very difficult to give a talk after exceptional, very nice presentation. So I have this burden, but I have to do it anyway, so please bear with me for the next 40 minutes. Today, I'd like to talk about three issues, or three items. Number one, how EDA and semiconductor industry have been working greatly to support the most exciting application of our time. We have been doing a good job, and I will show that to you. Second, how well are we, meaning EDA and semiconductor industry, how well are we prepared for the next big thing? I will claim that for the near term, next 2-3 years, we have some tricks to play with. We have some skills, some technologies in our bag so that we can deal with the next 2-3 years. But for the major revolution that we can expect in the next 3 to 5 years, we are not well prepared at all. And to make me even scary is not many people are paying attention to those essential things that we have to prepare to address the major challenges that is coming to us in 5 years time frame. And I'd like to share what I have in mind. The good thing of Keynote, by the way, as compared to presenting a paper, is you do not have to offer answer. When I was writing paper and giving a presentation, you have to identify problem, you have to identify methodology, i.e. algorithms, and data, and you should be able to claim that your method and result is a correct one, better than someone else's. The benefit of Keynote talk is all you have to do is pose problems, and answers will be found by someone else. That's advantage that I'm taking. Before I start, I'd like to congratulate the 50th Design Automation Conference. When I was young, it was around 25th, 26th, and I didn't see that EDA will continue to the 50th year. And I'd like to thank you all for coming to this 50th Design Automation Conference, but at the same time, to all those members who attended 49th, 48th, all the previous design automation conferences. So I suggest we give a big hands to all the participants now and previous DAC conferences. Let's give them a big hand. And I must tell you that I'm a proud member of Design Automation Conference. In my closet, I still keep that old t-shirt, which was given in 1990. If we look back at the papers in the proceedings of Design Automation Conference, we can see that DAC has been addressing the key, most up-to-date, most exciting topics at that time. 30 years ago, DAC 82, physical design, took most number of papers. 20 years ago, synthesis and verification. 10 years ago, DAC 2002, embedded systems, low power design. Last year, it was low power as well as thermal design and variation tolerance. So Design Automation Conference has been addressing the most up-to-date issues and has been leading the semiconductor industry. Now let's look at EDA industry from a little different angle, from business side. If we correlate the revenue of semiconductor business and revenue of EDA, we can see in general they are moving in the same direction, in sync, except for two periods. You can see from 96 to 98, semiconductor revenue has been stalled where EDA moved up. And 2001 and 2, we see the similar situation. Now, we can ask why. But if we move one level lower, if we divide semiconductor revenue into two classes, memory revenue, and system IC revenue, we can see that there is much closer correlation, much stronger correlation between system IC revenue and EDA revenue. So one good way of increasing EDA overall revenue sum is to encourage system IC business and vice versa. With that, let me start by asking this question. What field, what application is driving semiconductor industry? What is it that drives semiconductor industry and in turn EDA industry? If we answer this question, if we try to answer this question 5 years ago, clearly the answer would have been PC. But as you can see in this chart, now the answer must be different. Number of smartphones already exceeded the number of PCs in 2011, and number of tablets sold will exceed number of PCs sold in 2015. And about a month ago, there was a new forecast that even in 2013, this year, the number of tablets will be larger than the number of PCs sold. So the poor guy shown in the cartoon is not the only victim of wireless technology. There is another area that is suffering. And if you are in the mobile devices area, you are in lucky group. If we look at the smartphone or phone, cell phone, it started as a voice communication tool, but nowadays it's multimedia application tool with voice capability. And the 5 phone models that I show at the bottom of the slide gives us some hint. And I'd like to make 2 interesting observations in those 5 models. The first one is I-mode phone, which appeared in 1999. Until that time, everyone thought the cell phone was for voice communication. And when I-mode came out, and by the way, that came out from Japan. NTT Docomo supported that. When that came out, people were playing games with phones. When I was visiting Japan at the time, I saw people walking to the subway station by looking at phones. They are not talking to people next to them. They were just looking at phones and walking to the subway station. And that struck me. How can people do that? Nowadays, everybody is doing it, right? Even in coffee shop, when 2 people come together, instead of talking to each other, they take out their phone and they do something. So that started from 1999 when I-mode phone came out. The second interesting thing that we have to note is it has been only 6 years for the smartphone, a real smartphone. You know, we can say, even though there can be different opinions, we can say that iPhone was the first smartphone as we know it. It appeared in 2007, 6 years ago. And its strong competitor, Galaxy phone, came to industry only 3 years ago. So the smartphone, even though we think it's everywhere, still that field is a young field, at most 6 years old. Now let's take a look inside the smartphone. If we take out the cover, what will we see? We see at the bottom of the slide, you see big battery, because now you have a lot of applications to run, and you need big battery, whether you like it or not. Battery is there. And on top of that, you see a PCB board with many chips. The yellow, the chips marked with yellow cover are the important ones, and there are about 7. But if you have a great eyesight, you might be able to count the number of chips on the PCB board. I was able to count about 12 plus. This number is very important. We still have to use more than 12 chips, and in addition to many passive components to build a phone. Please remember that dozen, over a dozen. Oh, by the way, one thing is on the right bottom side, application processor is stacked with a mobile DRAM to reduce the space. Okay? I'll come to that later on. Now, if we look at the smartphone from application side, from user's perspective, we can see many interesting developments. One of which is more and more applications are offered or are required and offered by smartphone. As you see in the slide, voice command, location-based service, web browsing, and this year you saw that eyeball tracking, right, from smartphone. Lots of new applications which would require more powerful computing inside the smartphone. The second one is display. This year, we will be able to see smartphone with full HD resolution in our display. In about 2 years time frame, we expect to offer UHD level of resolution. Like, at the level of UHD, you cannot tell if it's real. When, I remember seeing a display of a picture in UHD. It's really difficult to tell which one is real, whether display is real or the real drawing is real. Really fine quality display. In about 2 years, we can expect to have that. Camera sensor, another good example. About 2005, 8 years ago, 1.3 megapixel camera was the best one in the cell phone. This year, there are high-end smartphones which offer 13 megapixel. And because of this development, effectively one market segment is totally destroyed. That is digital still camera. Now, you either carry your smartphone with camera or you carry very high-end DSLR-like cameras. No middle ground. So these are the kind of, in art's term, pull side. Users are asking these kind of things, and engineering team is delivering them. If we translate those users' requirements into the engineering terms that we can deal with, engineers can deal with, there can be many ways of capturing that, but I captured in 3 elements. Application on the right bottom side, more and more applications are required, as I said. Space limitation because of the form factor, and battery and heat problem that we have on the mobile phone. And for each problem, we as an engineering community, we were able to find the right solution. So let me talk about each solution briefly. Integration. There are I have 2 slides for integration. The number 1 is processing node, integration coming from the process node advances. It's very interesting to see that from 180 to 45 nanometer node, the new node was introduced every other year, 2 years, and we are familiar with the term tick-tock way of design. But from 32, if we count 28 as a separate node, 32, 28, 2014, every new node is introduced every year now. So the speed of development has increased by at least 2x. Another technology of getting better integration is packaging, 3D packaging. POP stands for package on package, and we have different ways of obtaining POP. Currently, as of now, laser drill process, LDP-based POP is most advanced one, and we are, I think, industry, including Samsung, we are developing through silicon via TSV-based POP. And I have a slide later on about TSV SiP. So much for the integration, and let's move to the processing power or computing power. This slide shows the achievement that we at Samsung have recorded so far from 2008. And the main message here is, even in smart mobile devices, in addition to the advantages that we can get from the silicon processing, we have to explore other areas to get or to gain more computing power. One example is 2010. You can see Cortex-A9 dual 1.2 gigahertz. When we had this device, one dual core, the first response we got from software team in the leading handset company was, why did you think about that? You guys are making our life miserable. You know, dealing with just a single core is good enough. And we believe, we meaning software team, we believe single core is good enough for cell phone. Why do you make our life complicated by offering dual core? But after they crossed that initial barrier, now dual core is industry standard. Unless you have dual core, you cannot play in the game. The same story applies to the quad core. And when we introduced the octa-core, the big.LITTLE architecture last year, we got the same thing. Hey, 4 is good enough. Why do you need 8? And why do you have to play with big and little? Now you'll see the one next, in the next slide. But eventually, when people learn how to play with those things, then they started to enjoy this new architecture. I studied computer architecture for my degree, and from computer architect's viewpoint, this is a great development. Now, even cell phone, smartphone has heterogeneous processor architecture. Now we are kind of opening a new door for the computer architecture team to optimize their solution for these mobile devices. Now let's touch the low power design and thermal aware design in the next 2 slides. The EDA community, like Design Automation Conference like you, developed many interesting new technologies, one of which is DVFS, that allowed us to control the temperature, the power consumption. One thing that we have to notice, and one thing that I like to report to you though, is there is another big avenue for power reduction. That is tight interaction between hardware and software. I went through some interesting experience during last 6 months, and that experience taught me that there is much more opportunity to get the optimized solution if you play both software and hardware at the same time. So I hope EDA community not looking at just the chip implementation, but looking at the software system as well in the optimization game. Now, thermal aware design, again, thanks to the ideas from design EDA community, we can now predict the skin temperature of the set, and we can control before the set reaches certain temperature. So, a lot of people, a lot of groups are working very hard to make things work. And sometimes we think, gee, this is about time to take a break. Unfortunately, the clock keeps ticking, and applications keeps asking for new things. So, what can we expect in the next 3 to 5 years in the smart mobile devices? Before that, let me ask this. Is there any other application that will drive semiconductor business in the next 3 to 5 years that will consume more wafers than smartphones or tablets in the next 3 to 5 years? I was asking around this question to many people, and the answer is no, not really. Still, smart devices are going to lead the wafer consumption. It's going to lead the semiconductor industry. So then, if that's the case, let's think about what we can expect. We can expect more and better applications and totally new applications like bio applications in the phone. Now, you must have heard this watch thing, which will add some bio applications there too. And clearly, we will see some better display as we covered before. How do we address those new applications or new requirements? I think we have at least 3 tricks to play in our bags. One is FinFET, the second one is Wide IO, third one is new architecture for display. Since FinFET is very well known and we have a father of FinFET in this room, let me just move briefly. But the thing is, FinFET is not free lunch because there is no such thing as free lunch. There is difficulty associated with that, and we have to understand them to really take advantage of the benefits of FinFET. Discrete design parameters, self-heating, those issues. Wide IO. This term has been around for quite some time. I remember hearing this term in my meeting with a Northern European company about 6 or 7 years ago. Conceptually, very beautiful. You know, if the communication bandwidth between logic or processor and memory is a problem, and as we get more complex applications, there will be more requirement for the memory bandwidth. So why don't you put memory on top of a logic device using thousands of connections? Sounds very good, but there has been very little action. Why? I think part of the reason is there was no semiconductor company which had control over logic devices, processors, and memory and packaging all together. To really enjoy this technology, you got to have those 3 technologies. And we at Samsung, luckily we had those luxury, so we built one. The leftmost diagram shows a conceptual diagram. The middle one is a picture of real chip, where you can see lots of micro bumps at the middle of the chip. The rightmost picture shows a test board. The red portion has a chip below that. So we have a working chip with wide IO capability, and we were able to measure some performance numbers, and it's very promising. In terms of bandwidth, compared to LPDDR3, which is the best one at this time, we can get about 14% more bandwidth, and power consumption number is really good. Compared to LPDDR3, the wide IO that we have consumes about 60% less power. Now, think about this thing. The temperature of handset became a big issue. Now people feel like, whether the cover is warm or hot, that's a very big issue. The heat dissipation is a big issue, and low power by 60% contributes a lot in the heat problem. If we consider the next generation, LPDDR4 and Wide IO 2, bandwidth is increasing by 1/3, whereas the power consumption is reduced by 40%. So this is a really good technology. Now, for this good technology to be able to find its time, we got to be able to play with software. And let me stop there in terms of software thing. Now, another kind of small niche thing, but still a very exciting, interesting idea is display architecture. I've never seen this kind of niche topic be covered in major conferences, but think about that. In typical case, which is shown in the leftmost block, AP or modem, whatever the main processor, sends display data to the display controller IC every time, every data. And if you look at third diagram, that shows the activity for every data. If you move, if you put memory inside display driver IC, which requires a new silicon processing technology anyway, but if you are able to put memory there, then all the AP has to do is just ship one set of data and forget it. The display data transfer will be done locally between memory and display panel. Even though this is a simple concept, look at the amount of power reduction it can bring to us. To the AP, up to the 90% in certain conditions. And in terms of battery, about 15% increase in the battery usage. Small idea, some difficult engineering work, which gives us a big return. So far I talked about 3 tricks that will address the next about 2-3 years. But then what? Is there any major revolution coming to us? And my answer to that is yes. And I'm afraid that we as EDA, as well as in semiconductor industry, we are not fully appreciating the magnitude of revolution that is coming to us. And let me show you what it is.
And we can actually bend the screen.
This was the first demonstration, at least public demonstration, of flexible display at CES show January of this year. Interesting thing though, and I must say that at that time, this was the only one, the only flexible display from Samsung. And audience really enjoyed to see that flexible display, as you could hear. Interesting thing is, since then, now it's beginning of June, during 5-month time frame, there were announcements from 2 other companies that they will have this flexible display too. So it's not any longer a special product. It's becoming a new product that will come to us. Now, with that in mind, I'm showing the current structure of a smartphone once more. With the PCB and back cover, what good is it if we have flexible display? What value does it add? None. To me, unless we change this PCB structure, electronic component structure, the flexible display is a good toy, but it does not add any real value to our life. So now display team, display folks prepared this nice thing. Are we, as a semiconductor community and EDA community, are we ready to take advantage of it? My assessment is, unfortunately, not really. We are still trying to figure out, how many more gates we can put in one black dot, one black box there, which is called chip. We are not worrying about how to reduce total number of chips into one. And I'm thinking of the term that I heard and I used a lot, which is called SoC, system on a chip. The promise there is whole system can be implemented in one chip. That's the idea of system on a chip. But as you can see over there on the PCB, still what we have is system on dozen chips, not system on a chip. So these are the potential conceptual diagrams of potential applications. The one extreme thing that I'm thinking of is like display as a handkerchief. You fold it, you put it in your pocket when you are not using it. When you need it, you take it out, you unfold it, and look at the display. Can we go there? So instead of giving out the detailed solution, I'm just throwing out wild ideas, what approaches we can take. If we look at wafer, it's not a very thick and firm thing. To begin with, it's firm, but if you grind the backside of it, it can be very flexible and very thin. So one idea is you grind the backside of it, make it flexible, and you glue the wafer to your flexible display. How you glue it, I do not know. Does it make sense? I doubt it, but that's an idea. So that's a good thing of giving a keynote, right? More practical approach, which I learned from display driver IC, is as follows. In all the cell phones that we have a display and something which we do not see. But if we take out the cover, there is thin chip, which is under the green box, thin chip, which is called display driver IC. If we can put all the chips and passive components into one chip, or at most two chips, then we can put them at that position, and we can have a flexible smartphone. Some people can say chip on plastic, and Art yesterday coined interesting term, SOD, system on display. But I think system on SOCD would be better. But somehow, the idea is we should be able to come up with a new way of integrating the system. And we should be able to find a way of taking advantage of this flexible display. We are not there. We are walking in one way, which has been good so far, but this way will not take advantage of new revolution that is coming from display. We may have to shift our direction to be able to address this challenge. Now, in the next about 3 slides, I'd like to share with you how Samsung Semiconductor has been addressing some of those challenges. As you know, we have industry's leading AP called Exynos AP, which incorporate many of the ideas that EDA community has generated. In addition, we have great display driver IC, image sensor, CMOS-based image sensor, and connectivity solutions. Then, we also offer great foundry service to fabless companies based on the ecosystem that we are building with our partners, EDA partners, IP partners, and so on. To support this business, we have invested a lot in the manufacturing capacity. 2 major manufacturing centers in Korea, and 1 big manufacturing center in this city, Austin, Texas, about 10 miles from here. With that, let me conclude by saying that EDA and semiconductor industry have been doing great job in supporting new, widely used applications called smart devices. It still has good technologies to solve the near term. But for the long term, we have to really revisit what we are doing and retune our direction if necessary. And I hope we, EDA community, along with process, marketing, software, and manufacturing, we as a group can create new features together. Thank you very much.